Recall that the trace of a function is the function we get when we fix one of the two input variables. When we look at the graph of a trace, we get something that ends up being a single variable function. And since it's a single variable function, we can apply our single variable calculus concepts to it. Specifically, it makes sense for us to ask about the slope of a function along a trace. And that idea is exactly what the partial derivative is. Definition: the first order partial derivatives of f with respect to x and y at the point AB are given by these formulas, provided that the limits exist. This notation can seem like a lot, but if you break it down, there's not really that much to it. Let's look at the partial derivative with respect to x. The first thing to notice is that this is a difference quotient. It's the evaluation of a function at two locations divided by the distance between those two locations. Here's what it looks like on the xy plane. We are evaluating the function at the points AB and a plus hb. The point AB is in one position, and a plus hb is to the right of it, a distance h away. If we look at what's happening on the y equals b plane, we get a piece of the curve, and the difference quotient is the slope of the secant line. And then we're taking the limit as h goes to 0 to get a derivative. This is called the partial derivative with respect to x, because we're only looking at how the function changes when moving in the x direction. The partial derivative with respect to y is the same idea, except now we're asking how the function changes if we only look at what's happening in the y direction, and that is the heart of what partial derivatives are. There are two notations for the partial derivative. We have presented things with the subscript notation. Notice that we cannot just use a prime to denote the partial derivative, because it doesn't indicate which derivative we're taking. Another notation for partial derivatives is known as the Leibniz notation, which is the notation that uses fractions. It's written with this fancy-looking d rather than a normal d to indicate that it's a partial derivative. We will never use the regular d for a partial derivative. When it comes to calculating partial derivatives, the key fact to remember is that you're treating one of the variables as if it were a constant. That comes from the fact that on the graphs of traces, we're fixing one of the variables to be a constant. This means that if we take the partial derivative of x squared y cubed with respect to x, we can factor out the y cubed part and just focus on the x squared part. Students sometimes make mistakes with the chain rule, especially when working with exponential functions. For the first few times you do these calculations, I recommend you take your time and write out the derivative with the chain rule step explicitly to help avoid errors. The first order partial derivatives are measures of the slope of a surface if you restrict yourself to moving in either the x or the y direction. If the slope for one of the variables is positive, then increasing in that variable causes the function to increase, and decreasing in that variable causes the function to decrease. If the slope is negative, then this is the opposite way around. And if the slope is 0, then there's no change. The nice part about this is that it fits perfectly with your previous knowledge about slopes. A more interesting question is what happens when you move in some arbitrary direction. At this time, we don't have any information about that situation, but it's worth trying to imagine how it might work. This is an idea that we're going to pursue later in this chapter. Sometimes you aren't given a formula for a function, which means you won't be able to use your calculus formulas to calculate the derivative. Instead, you may need to make estimates based on the given information. The two situations we're going to consider are when the function is described by a chart and when the function is described through contour lines. This is table 10.2.7 from the book. It is a chart of the wind chill in Fahrenheit as a function of wind speed and temperature. Let's suppose the wind speed is 15 miles per hour and the temperature is negative 10 degrees. Based on this chart, the wind chill is negative 32 degrees, which means that even though the air temperature is negative 10 degrees, it feels like it's negative 32 degrees. If we wanted to estimate the partial derivative with respect to v, we are asking how the wind chill changes as we increase the wind speed. If you look at the chart, we see that the next wind speed we have is 20 miles per hour, which is 5 miles per hour faster. In that span of 5 miles per hour, the wind chill drops by 3 degrees. So the temperature drops 3 degrees for every 5 miles per hour of increased wind speed. We can translate this into an estimate of the partial derivative. The partial derivative is negative 3/5 degree per mile per hour. This value is the slope of the line that passes through the 2 points on the graph. And that is the basic intuition of what it means to be a partial derivative. How much does the function change if you change one of the input variables by a small amount? Remember that this is not an exact derivative, since we're not actually taking a limit. We're just making an estimate. It's worth pointing out that there are multiple ways to estimate the slope. The process we just completed is known as a forward difference, and it's called that because we're using a forward step to estimate the slope. Another approach would be to use a backward difference. Notice that these two approaches will usually give different values. You can also do a central difference, which is when you use both a forward step and a backward step to estimate the slope. This approach takes more information into account and will usually give a better estimate of the slope. If you are working with a contour plot, the idea is the same, but you're going to have to work harder to get the values of the function. Here's the plot from the book. If you wanted to evaluate the function at 0, 0, you will need to observe that this point is between the contour lines of heights 3 and 4. You won't get an exact answer, but if you look at the location, you can see that it's a little closer to the 4 contour than the 3 contour. And so maybe this is about 3.7. This is a rough estimate, and that's just the nature of the problem. If you wanted to estimate the partial derivative with respect to y, you need to estimate the function at another point above or below it. You can know that the function is exactly 4 by going down to the contour line, but then you're going to have to estimate the coordinate. The same thing happens if you go up to where the function is equal to 3. Or you can move a distance of exactly 1 in either the positive or the negative direction, but then you're going to have to estimate the value of the function. There's no real way around the estimation, but whatever estimate you choose, to approximate the partial derivative, you need to set up a difference quotient. Partial derivatives are a key tool for the remainder of the course. Please take the time to practice the computational aspects of it and think through the conceptual aspects of it to make sure that everything makes sense to you.